Good afternoon. I hope you hear me and you see my screen, right? Yeah, I see that. Good afternoon, dear participants. I would like to present my work, Oscillation, Chaos, and Ordering of the Vortex Motion in Superconducting Nanotubes under Modulated Transport Current. We study superconductor open nanotubes with a small slit. Along this slit, we have contacts, and transport current comes in and comes out from these contacts, and we measure the induced voltage on these contacts. Usually we take niobium nanotubes with 5 micrometer length from 200 to 400 nanometers radius and 50-60 nanometer thickness. Also, an hour ago, Professor Fomin had a presentation where he discussed that such structures, if they are exposed in an external magnetic field, there may be different regimes of their work. For example, there we can see vortices or phase slips. In this talk, I would like to focus on vortices, which appear in such structures, and I would like to discuss several interesting effects which appear in such structures and associated with vortices, and what happens if we modulate a transport current with a small alternating component. First of all, vortices are nucleating at one side. They are moving along the nanotube and denucleates on the other side. We know that this generates induced voltage, and since vortices are nucleating and denucleating and they move non-uniformly, the induced voltage is not a constant value, but it deviates with time around its average value. And as Professor Fomin has already said, there are two characteristic times. The first time is the time of flight, delta T1, and the second time is the period of the nucleation, delta T2, and surely they depend on the magnetic field, the external magnetic field, and on the transport current. However, we can find such value of the magnetic field that the denucleation happens, for example, at the same time as the nucleation happens in the same half cylinder on the other side, or vice versa. We can find such value of the magnetic fields that the denucleation happens between two nucleations of the vortex. In the first case, we can expect that we know that the average number of vortices is more or less the same, and in the second case, the number of the vortices and an average number of vortices, it oscillates with time, and in this case, we can expect that the voltage oscillations are higher as well. It means that if we plot the standard deviation of the induced voltage as a function of the magnetic field, we can expect some oscillations in the amplitude of this alternating component itself. And if we model our nanotubes with time-dependent Ginzburg-Landau equations, we see that oscillations do appear, and these oscillations have a fixed period in some regions of the plot, and it means that the ratio delta T1 over delta T2 is a linear function of the magnetic field in this interval, which can be expected from the general theory. And an important tool that we use here is the spectrum of the voltage signal, and we calculate it numerically, but however, we can expect that such spectra can be obtained in experiment. And we have several interesting moments here. First of all, we have a main harmonic in the spectrum, which is plotted as a function of the magnetic field, of the external magnetic field. This main harmonic is associated with the period of the nucleation of our vortices. With green arrows point to the higher harmonics, and they are associated with the main harmonic because our system is nonlinear. However, we have at some point of the magnetic field, we have fractional harmonics and region of the chaos. These fractional harmonics are, for example, a half of the main harmonic or 1/3 or 2/3 and so on. And our question is, why does these fractional harmonics appear? To answer this question, we draw the trajectories of the vortex motion. And for example, if there's no fractional harmonic, there's only one path, one trajectory in each half cylinder. For example, this is the upper left panel. If we see the harmonic associated with 1/3 of the main harmonic, then there are three paths in each half cylinder. It is the bottom left panel, and this means that fractional harmonics appear due to the splitting of the trajectories. And for example, it happens then the first vortex, then it neglects, it chooses the first path, the second vortex chooses the second path, the third vortex chooses the third path, and then again the fourth vortex chooses the first path, and so on. If we take a smaller nanotube, for example, our previous slides were done for the nanotube with radius equal to 390 nanometers, and we had a chaos, we had fractional harmonics. In the case of the smaller nanotube with a radius equal to 240 nanometers, we don't have fractional harmonics at the same values of the magnetic field, and we don't have regions with chaotic behavior, as we can see on the left panel. And this appears due to the fact that our vortices are confined in a smaller region of the nanotube, and it has no freedom to move left or right as much as it had in larger nanotubes. And however, in this case, if we take smaller nanotubes, we can see the effect of steps and frequency lines. It means that at some value of the magnetic field, the frequency changes with step. If we studied why does it happen, and it appears due to a stronger interaction between vortices from one half-cylinder with vortices from the another half-cylinder. So it creates stronger correlation between vortex motion. Okay, and now we want to add a small modulation to the transport current density. It means that we add a small alternating component to the transport current. In this case, the amplitude of the alternating component is 30 times smaller than the direct component of the transport current. And in this case, we have so-called frequency locking effect if the frequency of the transport current modulation is close enough to the frequency of the vortex nucleation. And it means that in some region of, in some interval of the transport current frequencies, the nucleation frequency is exactly equal to the modulation frequency. Also, if the frequency locking appears, we can find it experimentally just plotting an average voltage as a function of the frequency, and this is a right panel, and we can see something very similar to the plot when we consider, for example, an anomalous dispersion in optics. So using a small current modulation, we can control the vortex nucleation frequency near the resonance. Also, very interesting to restrain or to suppress chaotic behavior in the vortex motion with a small modulation. And our modeling showed that it is really possible. Using a small modulation, we can suppress a chaotic motion if the transport current frequency is large enough. However, in the chaotic, in this case, which is presented on the slide, we also have a fringe of frequencies. You can see it on the right side of the left panel, and this happens to the effect of the voltage signal beating. Okay, so what's my what are my conclusions? First of all, vortex dynamics in open superconductor nanotubes is very rich and controllable by the magnetic field. The vortex motion in nanotubes can be studied experimentally using the induced voltage spectrum. Smaller nanotubes can find vortices in a narrower region, so there are less possibilities for chaos to emerge. The vortex nucleation frequency can be controlled with a small modulation of the transport current due to the frequency locking, and chaos in the vortex dynamics can be suppressed using the transport current modulation as well. Thank you for your attention.
Okay, thank you. So there is time for questions now.
I can't hear you.
Do you hear me? Hello?
I don't hear anything practically.
Can you hear me now?
Well, it is very silent.
Hi.
Yes. Hi. Now it's fine. Yeah.
Hi. Can you hear me?
Yes. I can hear you now.
Okay, so you hear me now properly?
Yeah, I hear you.
Great. So then there is time for questions now. So thanks for the talk.
Yep.
Anyone wants to start? So perhaps can I ask already a question? It's related to you discussed, let's say, the presence of chaos, no? So, and I think chaos is unwanted to some extent, the width dependence. But can you also comment on the length? And a question I had is, what are your boundary conditions? Are these normal metallic contacts, or is it really a superconducting boundary condition?
Along the nanotubes, where we have contacts, there are metal superconductor boundary conditions, and at the ends of the nanotube, there are free boundary conditions.
Okay, thank you. If I don't see questions, I can ask one more, because I had one which was not clear for me. Can you comment once more, let's say, the presence of these fractional Shapiro steps? For me, it was not clear how the bifurcation of the channels leads to fractional Shapiro steps. Can you explain that once more?
You mean these fractional harmonics?
Yeah, so here, and then you explained it like with the bifurcation, and I can understand, I see that, but how this comes back to measuring fractional steps was not clear for me.
You mean the appearance of the fractional harmonics with blue arrows? How does it related with different trajectories, right?
Yeah, because you have the same amount of vortices passing a contact. That was my confusion. Yeah, anyway, can you enlighten me?
Yeah, the process is the following. If we, for example, we had only one trajectory, and the nucleation of the vortices generated some frequency in the induced voltage. For example, we make a little bit larger magnetic field, and in this case, we have practically the same frequency of the vortex nucleation, but one vortex chooses one path, and another vortex chooses another path, and depending on the path, it can generate different values of the voltage. So, for example, one vortex generates a smaller voltage. Another vortex generates a larger vortex. And if we had, in the case of the one path, we had a usual sinusoid. For example, for simplicity, let's say that they are sinusoidal signals. In the case of two paths, one period is smaller and another period is larger. So that generates a new harmonic, which is which has twice smaller frequency.
Okay, thank you for, let's say, the small extra explanation. Keeping track of time, we have to stop here, so let's thank the speaker.
Thank you.